Welcome back, Chemistry 30. This is the fourth video, I believe, in EQ1.6. So we looked at concentration manipulations. Let's look at another concentration manipulation, increasing H2O. So if we take a look at where we were, H2O is on the left-hand side. So if I'm increasing it, adding more of it on here, so adding more on is going to get heavy on the left-hand side. So the teeter-totter will look like this. We have a bunch of H2O. So I'm going to want to use up or decrease the extra amount of H2O. And I do that by shifting to the right. So if you take a look here, it's heavier. You always want to go to the side that's lighter. Always make up enough to put it back into balance again. So products will increase. And reactants will decrease. All right. Concentration. Let's look at heat now. Increasing heat. Let's take a look. Heat, the kilojoule term, the 151 kilojoule, there it is right there. So you can see this is an exothermic reaction. Energy is on the right-hand side, meaning that it's produced, released. So if and again, think of this as an item. Think of it as a product. If I'm increasing heat, think of it like this. I added a bunch of heat on. Just like over here, if I added a bunch of water, it gets heavy on that side. If I add a bunch of heat, you can think of it as almost getting heavier on that side. So increasing heat, we want to do the opposite again. Decrease or the real terminology there is to use up extra heat. So in this case, it's going to shift to the left because, as you can see, it's heavy on this side, right? So I want it to go this way. So reactants, the side I'm shifting to is reactants. The side you shift to will increase. And products, the side I'm shifting away from, will decrease. All right, let's take a look at the last part here. Increasing pressure. All right, so the tricky one. Now with pressure, look for numbers of gas molecules. So look over here. If I look over here, here I have one C2H2 gas molecule. Here I have one H2O molecules. 1 and 1, 2 gas molecules. If I look at this side, I have an energy term and I just have one of these, one gas molecule. So that's the key thing you have to do first, is see what you have there. Okay, most of the time you'll have an unequal amount. One side will have more than the other. So if I go back to here, increasing pressure, again, the response is always the opposite. Decrease or use up extra pressure. So I want to decrease it. So the side that has a decreased amount of molecules the decreased amount of pressure is shift to side with fewer gas molecules. And that makes a decreased pressure, going to the side that has fewer molecules. So decrease means fewer. So of course over here, the side with fewer molecules is right there, product side. Okay, so we have fewer pressure. So less pressure on the right, more pressure on the left. So again, but take a look at what's happening there and then the side that we're going to increase to because of that. So if we're shifting to the right, products will increase and reactants will decrease. All right, last example here. What does changing the volume of the reaction have no effect? Remember, volume's the same thing as pressure. Well, it's vice versa, right? If we increase volume, we reduce pressure because more room means less pressure is going to happen with molecules hitting each other. It has to do with count gas molecules. So if I take a look over here, one gas molecule, solid, so that doesn't count. One gas molecule. Over on this side, here I have a gas molecule. Here, oh, that's a solid. So on the right-hand side, one gas molecule. Since pressure, so you can see, are of equal amounts, not like the previous example. Pressure depends upon unequal number of gas molecules. Since both sides are equivalent, no change in pressure. No change in pressure with that. You have to have an unequal number of gas molecules. Just like over here. The side that has more molecules, if we go to that side, it will be more pressure because more molecules hitting each other. If we have less molecules, if I force the reaction to go that way, it's making fewer molecules, therefore less collisions and less pressure. Okay, so we have changes in concentration, changes in pressure, volume, changes in heat, temperature. Technically, there's a fourth one. It's called catalyst. Catalyst, those of you from biology, lowers the energy requirements. So if you have a catalyst, it lowers the energy requirements for a reaction to occur, and vice versa for reversible reactions. The catalyst thereby increases the rates of both forward and reverse reactions. So what happens here is that equilibrium is reached quicker than without using a catalyst. The equilibrium value, the KEQ constant, is not affected. As a result, a catalyst increases the rate at which equilibrium is achieved. So you can think about this visually as, let's say I had concentration. So let's say I had this. Let's say this is a reaction in which I have A going to B. Okay? So A is getting used up, B is getting produced, and eventually over here, equilibrium happens here. The beginning of the flat line. Without a catalyst, it would look something like that. Okay? With the catalyst, it speeds up the reaction, right? So we could redraw it here. So concentration, again, it's A going to B and vice versa. So it may look something like this. And then here's B. So you can see equilibrium happens much sooner. Okay, so instead of equilibrium happening here with the catalyst, it happens quicker. Equilibrium occurs sooner. All right, so that's it, ladies and gentlemen. You could try the EQ 1.6 assignment, very similar to the examples we worked through. And there'll be another little assignment after that, but we'll talk about that in the next video. All right, we'll see you again.